Have you ever just watched a rocket launch, or even just a baseball flying through the air and wondered, how do we know exactly where that's going to go? Well, the secret isn't buried in some super complex math. Not at first, anyway. It actually starts with something way simpler: a ruler. In this explainer, we are going to build our understanding of physics from the ground up, literally starting with how we measure things and ending with a powerful way to describe pretty much any object's motion.
And that really is the bedrock of all science, isn't it? Before you can get to the mind-blowing discoveries, you first have to agree on how to measure stuff. It doesn't matter if it's the distance to a star or the weight of a tiny atom. If we don't have a reliable, shared way to measure it, every big idea would just get lost in translation. It's the essential first step.
So here's the big question. How do we make that leap from a simple statement like, hey, this table is 2 meters long, to predicting exactly where a satellite is going to be 3 hours from now? That's the journey we're going on today. We're going to connect that simple act of measuring to the beautiful, complex reality of motion.
So here's our roadmap. First, we're going to get comfortable with the basic language of physics. Then, we'll lay down the universal rules that everyone in science agrees on. After that, we hit a real game changer, the idea that some things are more than just a number. We'll see how direction is key, learn how to work with it, and then, finally, we'll put all those pieces together to chart the path of something in motion.
All right, first things first, the language of physics. Before we can describe anything complicated, we have to agree on the basic words and exactly what they mean.
So, at its very core, a measurement is really just a comparison. When we say a table is 2 meters long, what we're actually saying is that it's twice the length of this standard meter stick that we've all agreed upon. And every single measurement has these two parts. You can't separate them. A number, like 2, and a unit, like meters. One without the other is meaningless.
Okay, but for science to actually work across the whole world, we can't all be using different rulers, right? We need a universal set of rules, a common language that everyone can use for measurement. We need to keep the universe tidy.
You know, physics likes to keep things organized. It basically splits everything you can measure into 2 big buckets. On the left, you've got fundamental quantities. Think of these as the primary colors of our universe, basic, independent ideas like length, mass, and time. Then on the right, you've got derived quantities. These are what you get when you start mixing those fundamental colors. Velocity, for instance, is just length mixed with time.
So, the answer to that everyone using a different ruler problem is this: the International System of Units, or just SI. It is the global standard. This chart shows a few of the big ones we all agree on: the meter for length, the kilogram for mass, and the second for time. These are the official, agreed-upon building blocks for all of science.
But here's a little secret of science. In the real world, no measurement is ever 100% perfect. There's always a little bit of uncertainty. So to be honest about that, scientists use something called significant figures. It's basically their way of saying, look, these are the numbers I'm totally sure of, and this very last one, well, that's my best guess.
Okay, so we've got our units, we've got our rules for being precise, but now comes the plot twist. Because sometimes just having a number and a unit isn't enough to tell the whole story. Sometimes direction changes everything.
I mean, think about it. If you're just moving back and forth on a straight line, a plus or a minus sign is all you need to show which way you're going. But what happens when you're moving across a field or through the air? The real world isn't a straight line. For that, we need a much more powerful tool. We need to learn the language of vectors.
So here's the crucial difference. A scalar is just a simple number. It tells you how much of something there is, 20 degrees Celsius or 5 kilograms. Simple. But a vector gives you 2 pieces of information. It tells you how much, and it tells you which way. A push of 10 newtons isn't the whole story. A push of 10 newtons east, now that's a vector.
Let's make this super clear. Your mass is a scalar. It's just a number. But the force of gravity pulling on that mass, that's a vector, because it's always pointing down. When you're in your car, the speedometer shows your speed. That's a scalar. But your velocity is a vector, because it includes both your speed and the direction you're traveling. That which way part is what makes all the difference.
So, now we know what vectors are, but what do we actually do with them? How do we handle this extra piece of information, this direction? Well, let's dive in.
Yeah, adding vectors isn't quite like adding 2 plus 2. You have to account for their direction. One of the easiest ways to visualize this is the head-to-tail method. You just draw your first vector as an arrow,
Then, from the tip of that arrow, you draw your second vector. The result, the sum of those two, is a new arrow drawn from your absolute starting point to your absolute ending point. It's just like giving directions. Walk 1 block north, then turn and walk 1 block east. The vector sum is the shortcut right back to where you started. But we can also do the reverse, which is incredibly useful. Instead of adding vectors together to get one result, we can take a single complicated vector and break it down into simpler pieces. This amazing technique is called resolution. It lets us take any diagonal motion and split it into its pure horizontal part and its pure vertical part.
And why on earth would we do that? Because it's a game changer. It lets us turn one difficult two-dimensional problem into two much easier one-dimensional problems that we already know how to solve. Seriously, this is the key that unlocks our ability to analyze all kinds of complex motion.
And that brings us to the payoff. This is our final section, where we take all these separate pieces, all this theory, and we put it all together to describe the real-world path of a thrown ball.
Okay, this is it. This is where it all comes together. We've got our standard units, we understand this new language of vectors, and we've learned the secret trick of breaking them into simple horizontal and vertical parts. It's time to combine these tools and describe something real.
Now, don't let the letters scare you. This equation here is like a little time machine for motion. It's one of the core ideas in physics. All it says is that an object's final speed, v, is just whatever speed it started at, v0, plus how fast it's accelerating, a, multiplied by how long that's been happening, t. If you know where something started and how it's speeding up or slowing down, you can predict its future.
And this is where that vector trick becomes a superpower. To describe the beautiful, curved arc of a thrown ball, we don't use one super complicated equation. No way. We use two simple ones. The first equation just handles the steady horizontal motion, how fast it's going across. The second equation handles the vertical motion, which is constantly being pulled downward by the acceleration of gravity, which we call g. So here's the absolute biggest takeaway. That elegant, curved path of a ball isn't one single complex thing. It is simply a combination, a superposition of two much simpler things happening at the exact same time. It's just a steady cruise sideways, combined with an up and down motion that's affected by gravity. That's the whole secret.
So let's just trace our path one last time. We started with this simple active measurement and saw why we need standard units everyone agrees on. That foundation led us to vectors, a whole new language that includes direction. And with that powerful language, we finally unlocked the ability to break down complex motion into simple, manageable pieces.
And that leads us with one final thought. We've used all these ideas to understand a simple thrown ball. But just think bigger for a second. The orbit of a planet around the sun, the complex flow of a river, the precise path of a rocket heading to Mars. All of these can be understood using these exact same fundamental rules. The real question is, what else can this powerful way of thinking help us understand?